Okay, guys, I want to look at a free fall problem here with you, and I want to make sure specifically that you understand the difference between velocity and speed in this particular instance. So I've got a couple of equations here from your equation sheet. This is the third kinematic equation, the v final squared, and I've also got the equation for time here. And I'm going to use those to predict the amount of time it would take for this cannonball to land on the ground. So I've got a cannon being launched straight up from a height of 9 meters, and I want to predict the time that it lands on the ground. And I'll test that out with this simulation from phet.colorado.edu by placing this little time clock here. Whenever the cannonball reaches the ground, it's going to tell me the time, how far it's gone, and the maximum height that it reached. Okay, and I'm going to do that by first writing down each of the unknowns or the unknown kinematic variables that I can come up with based on information that I know about free fall. So for example, I know the acceleration is going to be due to gravity, and in the vertical direction, it's -10 meter per second squared, and I always know that value as long as we're on Earth. I also know that the cannonball is starting 9 meters above the ground. So its final position is going to be 9 meters below where it started. So I would say then the displacement is -9 meters. Okay. So one more piece of information that I can gather here, and that is the initial velocity is being launched at 18 meters per second. So I know the muzzle velocity of this cannon is 18 meters per second. Now, they're saying speed down here because that's just the speed that the cannonball is going to come out no matter what direction I launch this cannon, it's going to come out at 18 meters per second. Now, it's important for me to realize that I need to add the sign on these velocities, right? Speed is a scalar, it can't be negative, it's just the magnitude or the value of how fast that object is moving. When I do velocities, I need to determine if they're positive or negative based on their direction. So the fact that this object is being launched straight up, that is the positive direction. So I'm going to call the initial velocity positive 18 meters per second. Now I look at v final and time, and I'm looking through my equation sheet, and I say, well, there's no way to find time without knowing v final first. So I'm going to go and I'm going to find the final velocity first so that I can predict the time that this object's going to land on the ground. And I'm going to do that using this equation, v final squared is equal to v initial squared plus 2a delta x. Now, you'll see that I have all of that information already. I know the initial velocity, it's positive 18. I know the acceleration is due to gravity, so it's -10. And I also know the displacement, which is -9. And I'm going to go ahead and throw this into a calculator. Let's take 18 squared. Okay, maybe. 18 squared plus 2 times -10 times -9. And I get 504. So I can say then that VF squared is equal to 504, but I don't want to know what VF squared is. I want to know VF. So to get rid of that squared, I'm going to go ahead and take the square root of both sides, and I get VF is the square root of 504. So square root of 504. And my calculator is going to spit out a number. My calculator tells me that the answer is 22.45. Let's go ahead and round that at the hundredth place, and that's meter per second. Now, this is where we've left room for mistakes. And that is, in math, you might remember that anytime you took the square root in an equation, when you were solving for a variable, if you took the square root, you were supposed to write down positive or negative, right? The answer to this solution has two values, both positive 22.45 and negative 22.45. If you square them, you'll get 504. Now, often we forget to do that. We forget to choose between these two values, plus or minus. It's going to be really important for us when we're talking about velocity. Okay, remember that velocity needs a direction. And specifically for this object that's going to go up, turn around, and come back down and strike the ground, when it strikes the ground, it's going to be traveling in the downward direction. So the important thing here is when we talk about the final velocity, we have to make it negative. This equation will never, ever actually give us the negative. Your calculator is never going to help you out here. You have to be smarter than the calculator, and you need to assign that negative value based on the direction of the object when it slams into the ground. Okay, so that is a limitation of this kinematic equation. The calculator can never give you that negative. You need to be clever enough to assign it based on the direction that object is moving. So the final velocity here, I need to write negative 22.45. Now, in terms of the problems we do in positive physics, if they asked for final speed, this is like if I take a radar gun and I point it at the object just as it strikes the ground, then the radar gun is just going to tell me 22.45. Think about the speedometer in your car. It doesn't tell you what direction you're moving, it just tells you how fast. So this would be the final speed, and 22.45 is okay. But specifically when we need velocity, and especially keeping in mind that we're going to use it in this final equation to find time, it's really important that we assign that negative to that value based on the direction. So now when I go to find the time of flight for this object, I'm going to take the final velocity, which is negative 22.45, minus the initial velocity, which was positive 18, all divided by the acceleration, or negative 10. And I can again do that in a calculator. So I've got negative 22.45 minus 18, that's on top in the numerator, and I want to divide that by negative 10, and I get 4.045. So I'm predicting that this object will land in 4.045 seconds. Let's go ahead and test it out with the simulation. And launch that cannon, goes up, it stops briefly at the top, and it makes its way down to the earth. And if we go ahead and put our device here on the trajectory of that object, we get a time of 4.04 seconds, and that's when it reaches a height of 0. So that's when we know it strikes the ground, because now it's at a height of 0 from the Earth. So 4.04, we said 4.045, a very good estimate that matches the simulation from PHET. So just remember, when we're finding velocities, it's important for us to determine what direction and then to assign a positive or a negative. Okay, so good luck, and that's free fall.